Lecture 12, Concurrency, Synchronization, and Atomicity. We've introduced the concept of concurrency a little bit. We've said that this leads to various problems if we don't have some mechanism of coordination. That is, we don't have a way of figuring out whose turn it is and what is supposed to happen. So what we're going to talk about today in the subject of concurrency is synchronization. And synchronization is our formal term for that sort of coordination that I have referred to repeatedly, that idea that we need to make sure that things get along. Now, if the computer only ever did exactly one thing at a time, there would be no concurrency. If it was one process, one thread in the whole system, there's no concurrency, and therefore there's no concurrency problems. Any system that has multiple processes or multiple threads has concurrency, remembering that our formal definition of concurrency is that more than one thread or process could be making progress at the same time, or there are multiple things that are in progress at the same time. If the system is multi-core, we can have parallelism. That is, at any given instant, more than one thread or process might be actually executing on our hardware. Either one of those can lead us to various problems. We will talk about synchronization with no strong expectation as to whether there is parallelism in the system. All that is sufficient for bad things to happen is concurrency. It doesn't really matter that much whether we have a one-core CPU. If there are concurrent processes or concurrent threads that are trying to operate on shared data, it's bad. We will get wrong answers sometimes if there is not sufficient coordination. And so don't worry too much about whether a particular system has parallelism or not. All that we need is the possibility of concurrency, and then a problem could occur that we have to defend against. Our problem is mostly caused by this. The author of the application does not get to choose when a thread runs and when a thread switch occurs. Those are things that the operating system will decide according to its own ideas about what is supposed to happen and the order in which these things are supposed to take place. The operating system doesn't ask in advance, is it an inconvenient time? When the operating system decides your time is up, and it's someone else's turn. And there's no good way of telling the operating system, this is really important, please don't interrupt me. We can't do that. We have to live in a world where an interruption could come basically at any time, and we have to write our program in such a way that that interruption does not cause anything bad to happen, does not cause wrong answers, does not result in a concurrency problem. Now, the common English usage of the word synchronization usually means making two things happen at the exact same time. The commandos in the movie are hunched down outside the building and they say, let's synchronize watches. And that means that they are trying to make it so, the second hand on their watches all gets to 12 at the exact same time, at the exact same instant, so that everybody knows, after X minutes do this, at this time do that, and it makes whatever daring commando raid is the climax of this terrible action movie actually work. The synchronization relationship for the computer is not quite the same. It is in some sense a lot more general. What it means is there exists a relationship between events. Any kind of relationship between events, such as event A happens before event B. You could say event C happens during event D, and you could say that event E happens after event F. Either or any of those are fine. Synchronization just says there is an implied ordering to these things. So one of the implied orderings might be that if a course is a prerequisite, we would say, well, there is a relationship between the event of I'm going to take ECE 250, which is a prerequisite for this course, before I'm going to take ECE 252. There can also be things that happen during. You can have co-requisite courses, where it says, oh, you have to take this physics course at the same time as this electromagnetism course. That's a relationship that says during. At the same time isn't quite right, but during. You could also say, oh, 252 as a course happens during the 2B term. And then there are events that take place after, and that is, you can have ice cream after you finish your main course. That is a relationship. And yes, one of these examples is not quite like the others. But anything that is represented as a before relationship, where you say A happens before B, could also be written as B happens after A. I suggest, if you want to avoid confusion, you try to sort of pick a convention and stick with it. So make it easier for the reader. Okay, and there's two kinds of synchronization that I want to talk about, and they are not Summer Olympics and Winter Olympics, although I would forgive you for thinking so based on these pictures. But the first kind is called serialization, and the second is called mutual exclusion. So serialization is what is depicted at the top. We want there to be a defined order of events. We want to be sure that event A takes place before event B. We have, of course, done a little bit of this in the program world, but in the track running world, when you have a relay race, right, the person who's running first has to run and hand the baton over to the second person, and there is a definite order of what is correct. The first person has to finish their leg of the run before the second person can take the baton and run. If it didn't happen in that correct order, then your team loses, and you don't win the medal, and it's kind of embarrassing. That requires there is a defined order. So in the program world, we've seen this where we said, a process waits on a child process. There is a defined order. The child process has to be finished, and then the parent process is allowed to proceed. The merge sort algorithm that we just talked about in the previous lecture, if we have threads that sort the sublists, those have to be finished before the merge may continue. Thus, the sorting event A in that situation has to take place before the merging event B, or again, you could easily phrase it as event B must happen after event A. The other kind of synchronization that we have is mutual exclusion. And that is saying two things don't happen at the same time. So we call them event C and event D. They don't happen at the same time. And it's something that we have referenced on a few occasions, usually when I've said, we need some sort of coordination to prevent this problem, but I didn't get into it specifically. And that's what's shown on the bottom with the Olympic skier. And that is one person is skiing down the hill at a time. And ultimately, it's not that important if the Canadian athlete goes first and the US athlete goes second and the Russian athlete goes third, because all that really matters is they go one at a time. They won't both be on the ski hill at the same moment. And if it happened in a different order where the Russian person went first and then the Canadian and then the American, it would not be wrong. The order of those things is not important. What is important is that no two skiers are on the hill at the same time because, they could potentially crash into one another. In our discussion of interprocess communication, when we use, for example, shared memory, I've said, there is this danger that if you write into shared memory, it could be overwritten by some other process that's also writing into that area. This is a potential conflict, and what you really want in this situation is mutual exclusion, to be certain that process P1 is not writing into this shared area at the same time that process P2 is trying to write, or that at the same time that P2 is trying to read. Either way, these are both valid forms of synchronization, and they're not the same. The key distinction is that there is an ordering when we have serialization. There is an order, and there is an order that makes sense. And mutual exclusion just says these two things don't happen at the same time. So, the next slides go over the definitions of those. Okay, so we're going to try to get serialization accomplished through messages. Let's suppose that we have two people, Alice and Bob. I use the generic standard example names here because, well, as we continue through the example, don't want to get in trouble with the copyright police. They don't seem very nice. But let's imagine Alice and Bob work at the Springfield nuclear power plant in Sector 7G. They work in separate offices and they cannot easily see one another. Mr. Burns is a terrible employer, so they never get any days off, and there's only two of them, and Alice works the day shift 12 hours and Bob works the night shift 12 hours. And at least one of them must be on site at all times so that they're looking after the safety of the plant, because certain other more famous TV show characters are not doing a good job of that. So due to safety regulations, Alice is not allowed to go home until Bob has arrived, and the reverse is true as well, that Bob is not allowed to go home until Alice has arrived. But we'll just focus for right now on Alice being the one who is there and wants to go home, and Bob is the one who is arriving. So this scenario obviously illustrates serialization. We have a defined order of events. There is a known order, and it is Bob arrives, and then Alice leaves. A different order would be wrong. It would violate safety regulations. So, how do we get that behavior? One of the drawbacks of doing this by video as opposed to interactively is that these topics, especially when we talk about serialization, synchronization, concurrency, provide a lot of opportunity for you to think about the answer in a classroom setting and suggest to me a solution. And I'm sad that that's not an option right now, because it is helpful to have a minute to think about it and to come up with a solution, and then we'll talk about whether it is a good solution. So for the moment, just think about it, and then I'll reveal the answer. Okay. The simple solution is, well, a message of some sort. Alice won't leave until she gets a message of some sort, a call or a text or something from Bob saying Bob has arrived at the office, and Bob doesn't call until he's arrived at the office. So when this condition is fulfilled, Bob has arrived, then Bob will send a message, and that is something that Alice has been waiting for. This is a very simple scenario. Message passing is, however, a valid solution for a lot of synchronization problems, and it's the sort of thing that we do in real life quite a lot. You tell a friend, text me when you get here, or you tell your parents, call me when you've finished, something like that, which is you are waiting for something, but you will basically just ask the other party to send you a message when the certain condition is fulfilled. If we're certain that Bob arrives before Alice departs, we could say that these events are sequential because we know an order of events, right? If everybody agrees to the rules, if everybody does what they are supposed to do, then events happen in the correct order and they are sequential. Suppose, though, we have different events that don't have any mechanism of coordination. So at some point during the workday, Alice eats lunch. And at some point before Bob gets to work and before the shift change, Bob also eats lunch. We don't have any idea, based on what we know so far, who ate lunch first, so we would say that they ate lunch concurrently. This differs again a little bit from the normal, plain language use of the word concurrently. The formal, strict definition of concurrent in a computer program is that two events are concurrent if we cannot tell by looking at the program which will happen first. Another way of phrasing that is if there is no coordination mechanism that enforces an order on these events, we don't know what order they happen in, so we would say they happen concurrently to reflect the fact that we don't know the order. Usually, when we say something happened concurrently, we say it happens at the same time. So if you look at the clock, Alice and Bob both had lunch at 12 o'clock. But concurrency in the program is not this. What it is it's saying we don't know the order of events, and more importantly, we cannot guarantee an order of events. It is possible in this scenario that Alice had lunch at 12 and then Bob 1 hour later, or they both ate at noon, or Alice had lunch at 13:30 and Bob at 12:15. We don't know, and there's no enforcing of ordering of that. There's no rule that says that Alice has to eat lunch before Bob, and there's no coordination that makes that always the case. One of the things that this means is that on different days, they could eat at different times. Maybe today Bob is hungry earlier and he wants to eat at 11, and maybe tomorrow he's not that hungry, so he eats at 12:30. That is okay. The order of events that are concurrent could change on two different runs of the program, and that's something that we call non-determinism. And non-determinism is just a fancy way of saying that the outcomes could change based on factors that are either outside of our control, random, or just not well known. In a non-deterministic program, you can't tell just by looking at the source code what the execution order of events will be. If you have two concurrent events, one of which where a program prints 1 to the console and the other where it prints 2 to the console, these could happen in any order, so you might see the output as either 12 or 21. Unless we explicitly put in a form of coordination where we put in a rule, we enforce that rule using serialization and using our synchronization mechanisms, we could get either output. Maybe you don't care. Maybe it's not a problem what order these things happen in, and it's not wrong to see 12 and it's not wrong to see 21. However, if 12 is correct and 21 is wrong, then finding that and fixing it could be quite difficult. It might be very painful. Concurrency problems like this can be difficult to debug, and they might occur very rarely to begin with. So it might work perfectly fine when you run it on your machine. It might work fine, with the automated tests. But then things go wrong, for 1% of customers when they're trying to use the system. This is what is referred to as a heisenbug. This has nothing to do with the Breaking Bad TV show, and everything to do with the physicist pictured on the right there, Werner Heisenberg, the one responsible for the scientific principle of uncertainty. If you remember what that is, the uncertainty principle says that the more precisely that you know the location of a particle, the less you know about its momentum, and the more that you know about its momentum, the less you know about its position. And of course, if you know exactly its position, you know nothing about its momentum, and so on. And yeah, it comes from this principle of uncertainty, because the Heisenbug is the kind of bug where when you try to track it down, it becomes somehow less likely to occur. Why does that happen? Okay, you want to track it down. You think, okay, I'm going to use the debugger. Thing is that a Heisenbug is effectively a timing problem, right? Things happen, and if they happen in the right order, nothing bad occurs, all the output is correct. If they happen in the wrong order, then some bad side effect is observed, whether that's just things are printed wrong, or whether program data is lost, or there's a crash. You don't know. So when you open up the debugger and you are going to then run the program under the supervision of the debugger, its behavior is different in terms of timing. Debugging is slower than normal execution, even if you're not stepping through it one statement at a time. Obviously, if you step through it one statement at a time, for sure it is different. But whatever you do in that case, you are running the program a little bit differently, and you might not see the problem because the timing is always consistent as a result of the fact that when you run it in the debugger, the timings are slower. By that same token, if you wanted to debug using print statements or something to that effect, same thing. If you add a print statement that says the value of x is this, well, the print statement takes work to do, and it changes the execution time of the thread, and it might cover up the problem. So those kinds of bugs are very frustrating to debug. A normal bug where the formula used is wrong, it's wrong every time. You can run it in the debugger as slowly as you want, and you can see, oh, here's somebody forgot to put this thing in brackets, and bed mass doesn't work as expected, and you end up with the wrong answer. That's consistent. That's not a heisenbug. But these timing problems are heisenbugs, and debugging them is significantly more difficult as a result of the fact that trying to track them down makes them less likely to occur. So here's a quick example of shared data and atomic operations. We've noted more than once now that interprocess communication is required when we have an area of memory that is somehow shared, whether that's shared between threads or shared between processes. So we have a very simple example here in which we have two threads, thread A and thread B, and for a lot of what we're going to talk about in the topics of synchronization and concurrency, we're going to just use a simple C-like pseudocode as our mechanism for dealing with it. It makes it a little bit easier to reason about by sort of stripping away extraneous details and open curly braces and parentheses and what have you that we generally don't need. And it also allows us to, if we're writing it by hand, just be a little bit more compact. So here's a shared variable x, and it is manipulated by two threads A and B. We have no mechanism of coordination between A and B, so what are possible outcomes when these threads run? Again, I'll give you a minute to think about that. Okay, so you should have come up with some different possibilities. First one is that thread A runs to completion and then thread B. So x is assigned 5, 5 is printed, and then x is assigned 7. So if you consider all possibilities based on what is printed as well as the final value, this is, the final value is 7 and the printed value is 5. Okay. Now, another possibility is that thread B runs first, so x is assigned 7, then it's overwritten with 5, and then print x takes place, so the final value is 5 and the printed value is 5. A third possibility is that x is assigned 7 happens in between the x is assigned 5 statement and the print x statement. So x is assigned 5, then x is overwritten with 7, then x is printed, and so the signed final value is 7, and the printed value is also 7. So that part is something that we can't know in advance because there's no mechanism of coordination. What we can know in advance is there's no possibility that the final possibility that we hadn't discussed is that 7 is printed and 5 is the final value occurs. And why is that? Well, that happens because we're always certain that statement labeled A1 takes place before the statement labeled A2. Any individual thread always executes sequentially. So thread A executes statement A1, then A2. If there was an A3, that would be next, then an A4, and so on and so on. And thread B would execute statement B1, and then B2, and so on and so on and so on. But we don't know, given what we see here, where in relation to thread A that B1 statement happens. So it could be before A1, it could be between A1 and A2, it could be after A2. Any of those things is sufficient. Any of those things is possible. So we don't know. We don't have a good mechanism of coordination, and that might be a problem. So, good. Now, we should also be aware that we don't even really need multiple threads to have a concurrency problem. Just having interrupts in the system is sufficient. If I go back, one way you could look at that is if instead of thread B, this was interrupt handler, instead of being a thread, then if the interrupt fires here before A1, or between A1 and A2, or after A2, all of those result in different things. But consider an application that is used to count occurrences of some event. I don't know, that maybe seems familiar from the last video. And we'll store the count in a variable called count. It might have previously been called sum, but it doesn't matter very much. It's all the same. But this time we will add some facility for the user to reset the counter. So we'll give them a reset button of some sort. So we're going to count events. Every time we detect that that event occurs, we increment count using a statement count plus plus. That seems like it is one single statement, but here's the thing about count plus plus. It is more complicated than it might look like. Just because it is one line of code in a C program doesn't mean it is a single operation. Count plus plus is officially read, modify, write instruction. And that is, if count is 4 and we increment it, there are 3 things we need to do to make the increment work correctly. The first one is we have to read the current value, then we have to add 1 to it, and then we have to write the changed value back to wherever count is stored, so memory somewhere. So that simple operation, it looks straightforward, count plus plus, is really 3 steps. And you know that if you think about, how do you increment a counter, you have to look at the current value and increment it, and that requires a little work. Okay. So now imagine that the interrupt for the reset comes at the worst possible time. The interrupt is supposed to set the value of count to 0. So let's break down the steps. Number 1, read the current value. So we read 4. Add 1 to the current value. Okay, interrupt happens here at step 3. And the interrupt handler writes 0 to the variable, so 0 is written. End interrupt, so our interrupt handler is done and control returns to where it was before the interrupt fired. And then the next step is write the changed value back to memory. So we write 5. Okay. That's not what was supposed to happen. That's not what was supposed to happen. The variable count at the end of the sequence has a value of 5. It should be either 0 or 1. The user pressed the reset button, but actually nothing happened. The reset action was ignored, or the reset was lost. If the reset had come at a different time, if it had come before, say, reading the value of the variable before we read 4, then the final result would be 1. If the reset interrupt had occurred after writing, then we would have 0. Those would be okay as outcomes because the reset operation still took place, but the reset action here got lost. Okay, what do we do? How do we deal with that? What do we know for our tools that would help us to solve that? Okay. So our problem arises in this case because the instruction of count plus plus is actually 3 separate operations, and these could be interrupted at any time. So we might have completed 1 of the 3 operations, or 2 of the 3, or 0 of the 3, or all of them, and the interrupt could happen at any time. So sometimes what we want is for an operation to not be interruptible. And when we are performing that kind of operation, we say that operation is atomic. Or if we want a set of operations to all happen uninterruptibly, we want that operation, or that set of operations, to be atomic. Why atomic? Well, it comes from a Greek word, atomos, roughly meaning not cuttable, a being the negation prefix and tomos being cuttable. Not that I actually speak Greek, but that's the explanation about it that I read. Although since 1945 we have been able to split the atom, thus proving that atoms are divisible and humans are very good at finding ways to make things explode, this not divisible property is what we're looking for. And we'll find out that as we get through our concurrency topic, there exist atomic operations in a given system. That is to say that there are some things we could do that we know will not be interrupted part way, but you absolutely cannot be certain that all operations are indivisible, and you should assume that the opposite is true. You should assume that every operation is divisible unless you have a reason to know otherwise. If the specification of something tells you it is atomic, then you can believe it. But just because something is a single statement in your program or a function call or anything like that, you cannot rely on that necessarily being indivisible. You have to check to be sure. So, could we get what we needed here with serialization? Can we make sure that the count plus plus operation completes before the count is assigned 0 operation? Because if we did that, it would mean that the reset would not be ignored. The answer is this tool is not the right one for our needs. There's no obvious order between the events. The user is able to press the reset button at any time, even if no events have occurred, even if an event has not occurred recently, even if an event is about to occur. Similarly, whatever event we are detecting could be detected even if the user is nowhere around. The user's gone to bed, they're not staying up all night, and they're not going to press the reset button anytime soon. There's no clear ordering. And that means that serialization is not the correct tool here. What we actually want is something else. The serialization concept requires that there exists a correct order. First this, and then that. What we need is mutual exclusion. That is the downhill skiing kind of model for this mechanism. We need two things not to happen at the same time, but we don't have to enforce a specific order. Here, where both orders are valid, we use, mutual exclusion, which is also sometimes referred to under the term mutex. Mutex is also used in general in our programming for the kind of locks that we want to use when we get there soon. But in this case, the key distinction is that we don't enforce any particular ordering of events. All we're interested in is making sure that, for example, we don't have more than one thread trying to update a variable at the same time. So an action to reset count to 0 has to wait until count plus plus is completely finished, or vice versa. The assignment to 0 has to finish before the count plus plus operation gets to execute. All right. Put your deerstalker caps on, also known informally as the Sherlock Holmes hat, and we are going to be detectives in this. We've identified, generally speaking, the idea of shared data as a potential source of error, and throughout this part of the course, I'm going to present you with some pseudocode implementations of things, and I'm going to ask you to examine them carefully and find out and make a determination about whether they are correct or incorrect. And we have to actually go to a definition of correct and incorrect before I go on. But incorrect would be something like we do not get the correct answers, we do not get the behavior we are supposed to get, all of the threads get stuck. Any of those outcomes are bad outcomes, and I'm asking you to look at something and tell me, is a bad thing going to happen, or could a bad thing happen? So keep your detective hats on. Now, if we have a section of code that should be accessed by a maximum of one thread at a time, that is referred to as a critical section. And the purpose of mutual exclusion is to ensure that at most one thread is in that critical section at a given time. If that rule is not enforced, and we have more than one thread in that section at a time, something has gone wrong. We have a problem in our program. It is a programming error or design error of some sort, and it needs to be fixed. On the other hand, the critical section is supposed to do something useful. It serves a purpose. You didn't just put it in the program for fun. So you cannot solve the problem by never allowing any thread to access it ever, right? That would not be a valid solution either. It's the responsibility of the programmer to identify what critical sections, if any, exist in the program and protect them with mutual exclusion constructs. Some analysis tools may exist to identify shared data, but ultimately these tools are not as good as you taking a careful look and deciding whether something is shared or not. Critical sections should be as short as possible, but not so short that they leave important things out. They do have to enclose all of the shared data accesses, and I say accesses quite specifically because this does include both reads and writes. And why is that important? Well, the critical section is something that can't be run in parallel, so it increases the magnitude of the S term in your program, meaning the speed increase that you get from having parallelism is reduced. And more than that, it's impolite to make other threads and processes wait unnecessarily. I'll take a minute also to point out here that although we frequently say the critical section as though there is exactly one critical section, it is likely the case that there are multiple critical sections in your program and they are protected separately. So a thread could be in critical section X while a different thread is in critical section Y, and that's okay. For now, we just want to think about one critical section because that's the simplest case, but just keep in mind that there could be more in the program, and that's not a problem. So let's look at our first example, and it is mutual exclusion via flags. In particular, flags is a turn variable. And so on the left, we have thread A. Thread A waits while turn is not 0, just spins in a loop. Once turn is 0, it breaks out of the loop, enters the critical section, and at the end assigns turn to 1. And thread B is effectively the same, although a little bit different, which is while turn is not 1, wait. When turn is 1, it breaks out of the loop and enters the critical section and assigns turn equal to be 0. And this is a strict alternation scheme, so thread A takes a turn, then B, then A again, and so on and so on. And I want you to take a look at this, and I want you to tell me, does this work? Does this accomplish what we need for mutual exclusion? Okay, the answer to this is, well, no. This is not good as a solution because it requires a couple of things. One is that each of these threads, A and B, wants to run exactly as much as the other, so they always take turns. What if thread A is supposed to run more often than B? Why isn't that allowed? Similarly, if thread B terminates, then actually A is stuck forever because the variable will never be reset, because it will always be saying it is thread B's turn. So I don't like that. This is not valid as a solution. Okay, let's try this instead, the second approach. Thread A checks while busy is true, wait for my turn. When busy is false, we'll break out of the loop, assign busy equal to be true, and then we'll have the critical section. When we're done, we'll set busy equals false, and B actually does exactly the same thing. The code is identical on both sides. So we're using a Boolean flag now. Does this work? Does this work? Well, I say that the answer is no. The problem that we have is that this statement while busy equals true is followed by an assignment statement. So we have while busy equals true in thread A checked on line A1, and then busy is assigned true is set on A4. It is possible that a switch between A and B happens between the read and the write. So A1, while busy equals true, this evaluates to break us out of the loop. But before statement A4 happens and busy is assigned to be true, thread B gets a turn, it checks, busy is false, breaks out of the loop, and then it also proceeds to statement B4, enters the critical section. At some point, thread A gets another turn, busy is assigned true, enter the critical section, and we have both A and B in the critical section at the same time. So this solution is not satisfactory. That's not okay. we couldn't use this. It doesn't work. Okay, let's have an array of flags. So A sets flag at index 0 to be true, and then while flag at index 1 is true, we're going to wait our turn. When that's false, enter the critical section, set flag at 0 to be false. Thread B is the complement of this. Flag at index 1 is set to true, while flag at index 0 is true, wait our turn. Then, when we break out of that loop, enter the critical section and set flag at index 1 to be false. How about this? How about this? Well, I'm sorry to say that this one doesn't work either. This is also defeated by an untimely process switch. Can you see where that happens? Yeah, if statement A1 happens and we set flag at index 0 to be true, and there's a thread switch over to B, and flag at index 1 is set to true, then when we get to the while loop here, well, B2, we're going to wait in this loop forever, and when we switch back to thread A, it gets to the while loop, and flag at index 1 has been set, so it's going to wait in the while loop forever. And both threads A and B are now in their respective while loops that they can never get out of. Okay, so both processes are stuck. Neither thread is able to advance because each is waiting for the other, and that's not happening. They won't be able to get to the statement that assigns the flag to false, and therefore all the threads are stuck, and they're stuck forever. This might actually be, in your opinion, slightly better than having two threads that are in the critical section, but having both of these threads stuck is not okay, and keeping threads out forever is not acceptable. Okay, so all of the attempts at a solution that we have looked at so far have basically been foiled by an untimely process switch. This is triggered by an interrupt. We've said, if everything happens, in a good way, where we are lucky on something like this, thread A runs to completion, then thread B runs to completion, and everything is fine. It's only if we have a switch between A and B that the problem occurs, and even then, only if it occurs at an inconvenient time, right? If we had a switch between these processes, at the critical section stage, well, it would be this thread just keeps waiting, and then thread A resumes. Nothing bad came of it. This does perhaps make you think of a possible solution, and that is, let's disable interrupts. And disable interrupts is, turning off the fire alarm. Why would you ever want to do that? If interrupts is disabled, then all interrupts are disabled, and that includes the ones from the user. So, when you as the user want to type something, you press keys, and keys generate interrupts. So those are getting ignored right now. I don't think you like that. And thread switches the scheduler would perform will also not occur, which I guess was the objective. But the system can't respond to user input or any other events for that matter, detecting a fire or detecting an incoming missile or something like that. And if an error is encountered and the program dies while interrupts are disabled, the system is basically stuck and other programs will not be able to run. So that's not cool. This is fine. Everything is fine. Just ask the dog. So I don't think we would consider this to be acceptable. But even if you said, actually, I don't care, the house being on fire is completely fine, and, I'll just wear my burn-proof pants, actually disabling interrupts is not sufficient. Why is it not sufficient? Well, if you have a multi-core processor, then it doesn't matter if there's a process switch. It doesn't matter if there's a thread switch, because threads A and B could be executing just independently on different cores, and we can't stop that. So this kind of behavior isn't working for us, and disabling interrupts is not the solution. But actually, maybe you're on the right track if you said we need to get hardware involved. What we actually want is the ability to read and maybe write a variable all in one atomic, therefore indivisible operation. And the hardware designers were aware of this kind of problem and have kindly provided a facility that helps, and that is the test and set instruction. Okay, what is the test and set instruction? It is a special machine instruction that it always runs within one instruction cycle and is therefore not interruptible. And it is an atomic read and possibly a write, depending. This slide shows you the description of how test and set works using the C programming language. I do not want you to think for even one instant that this is actually how test and set is implemented. It is not a function, and it does not work like this. If you just wrote a function, boolean, test and set, this, that, and you said, I compile this and I run it, it would not be atomic because it is, of course, composed of multiple statements and is interruptible just like anything else. Why do I use this description? Because this is a very precise way of telling you what test and set does. If I didn't do this, I would give you a paragraph of text that says, well, the test and set instruction, checks the pointer I, and if it's 0, it assigns it to 1 and returns true, else it returns false. And unfortunately, English is imprecise as a language. And that's really true of any sort of human language, but it's imprecise as a language, and therefore there would be some room for interpretation about what did I mean, and where does the if block end, and where does this clause end. That's not okay. This is why legal documents are really long and really boring, because English is imprecise and the law wants to be precise, and therefore a great deal of time and attention has to be spent on defining precise meanings of words and precise meanings of phrases, and then composing a sentence in such a way that it is unambiguous. That's also why it's very difficult to just write a programming language that resembles English, because, or resembles any other natural human language, is because language is imprecise and the computer can't handle that. It doesn't know what you want if you don't express your request extremely literally. So that is the purpose of the C language description shown here. It is a very precise way of telling you what test and set does. And in one single hardware instruction, it will try to change the integer pointer that we're looking at from 0 to 1. If it was successful, it returns true. If it was unsuccessful, it returns false. It would be unsuccessful if somebody else had already changed it to true. Now, this test and set routine, as I say, is a hardware instruction. So, and because it's uninterruptible, if you have multiple threads that try to call test and set at a time, only one will succeed. One and exactly one of the callers will succeed. Everybody else gets back false. If you did succeed, you successfully changed the integer here from 0 to 1 and returns true, and that's how you would know it is your turn, that you have succeeded. So actually, to make this work, we'll put it into action. And here we have some code. Both A and B would be the same, so I have spared you the reproduction of the second part. But it is while not test and set busy, then we'll wait. When we break out of this loop, we will enter the critical section. We will assign busy to be 0 when we are done. The implementation for B is exactly the same. So yeah, we will repeatedly try to call test and set. In this case, don't think of test and set as a function, but remember the compiler will turn this into an atomic hardware instruction. And if we were successful in changing busy from 0 to 1, we break out of the loop. If we were unsuccessful, we'll wait and try again. Once we've done that, we enter the critical section. When we're done, we can set busy back to 0. You'll notice that assigning busy to 0 is a normal standard assignment statement. There's no test and unset. That is because it doesn't matter. Test and set is about changing the variable from 0 to 1, and if we do that, we enter into the critical section. If we fail, we don't. When we're leaving the critical section, we need to set busy back to 0, but if we were the only ones who entered the critical section, we'll be the only ones who got to the statement busy is assigned 0, and therefore there's no cause for concern. There's no reason why we have to contend for whose turn it is to assign busy to be 0. That happens once and only once. Okay, this test and set routine, I won't tell you to examine it and tell me if there's anything that's wrong, because we've already established it's good at what it does. It is suitable for purpose. So finally, we have something that provides mutual exclusion without the risk of things getting stuck. Stuck in this case being, each thread is waiting for the other one to exit the critical section, but neither of them is in there. This is good, but it could actually be improved. This while loop that's on the previous slide means that we're constantly checking the value with test and set, and that's what's referred to as busy waiting. And busy waiting is kind of a waste of effort. A given thread is not getting into the critical section any faster by repeatedly checking, is it our turn? And is it now? Now, are we there yet? Are we there yet? And just like an annoying child in the back seat, the more the child asks, "Are we there yet?" It doesn't make you get there any faster, but it is irritating. So, could we improve on that? Is there a way that we could get around that? Not constantly check to see if it is our turn. Perhaps as a first idea, you thought about, well, what if we just kind of wait a little while and then we'll come back to it? So put a sleep instruction or something in there that says, we'll just wait, come back again later. I mean, that's what you would do if you wanted to, buy ice cream or something. Imagine you're allowed to go outside again and there's a truck that sells ice cream. It's like, well, if the lineup is long, why don't you just check again a little later? Come by again on your way back. Maybe the line will be shorter and maybe it will be fine. However, maybe that's not optimal for what we want. It is probably better to use messages, because we can use messages to get serialization. We had this sort of behavior of when Alice calls Bob, then Alice is sending a message that says, "I've arrived, you can leave." And when Bob calls Alice, again, that's the serialization, where there is a defined order of events. That's the model. Can we do that with mutual exclusion? And we will find, of course, the answer to that is yes. There is a way that we could achieve our goals for mutual exclusion without busy waiting through the use of messages, through the use of communication. However, that's going to be in our next topic, so I invite you to think about that a little bit between now and the next video. You might choose to watch it right away, but if you don't, then just between now and then, you should think about it a little bit and see if you can come up with a mechanism for that. Otherwise, I will see you in the next video.